In this video, we'll build an intuitive picture for single slit diffraction, and then solve two numerical problems. First, a minimum angle, and second, a slit width from a known secondary maximum. Let's first see the geometry. Light comes in as plane waves, reaches a narrow slit, then spreads or bends around the edges. That spreading creates a bright and dark pattern on the screen, a wide bright central maximum with alternating dark and faint bright regions. Two key relations govern the angles of dark and secondary bright spots. For minima, a times sine theta equals n times lambda, where n is 1, 2, 3, and so on. For secondary maxima, a times sine theta equals quantity n plus 1/2 times lambda, where n is 1, 2, 3, and so on. Example 1. A wavelength of 600 nanometers passes a slit of 0.1 millimeters. At what angle does the first dark spot appear? Given values, lambda equals 600 times 10 to the minus 9 meters. The slit width equals 0.1 times 10 to the minus 3 meters. For the first minimum, n equals 1. Use the minima relation. A times sine theta equals n lambda. Solve for sine theta. Sine theta equals n lambda over a. Substitute numbers to get sine theta equals 6 times 10 to the minus 3. That is 0.006. As a helpful estimate, for small angles, theta is about sine theta. So theta is about 0.006 radians, which is about 0.34 degrees. Example 2. The second secondary maximum is observed at 30 degrees using light of 500 nanometers. What is the slit width? Given theta equals 30 degrees, lambda equals 500 times 10 to the minus 9 meters, and n equals 2 because it is the second secondary maximum. Use the secondary maxima relation. A times sine theta equals quantity n plus 1/2 times lambda. Solve for a equals quantity n plus 1/2 times lambda over sine theta. Substitute. A equals 2.5 times 500 nanometers divided by sine of 30 degrees, which equals 2.5 times 10 to the minus 6 meters. That is 2.5 micrometers. Let's mark a larger 30-degree ray on the diagram for context. To summarize, dark spots satisfy a times sine theta equals n lambda. Secondary bright spots satisfy a times sine theta equals n plus 1/2 times lambda. Carefully identify the order n, plug in values, and solve for the requested quantity. Visualizing the geometry with a reference ray makes the angles more intuitive. Welcome to Diffraction Numericals for Grade 12. In this video, we will quickly review the 3 single slit diffraction formulas and then solve 3 problems step by step, one for the linear width of the central maximum, one to find the slit width, and one for the angular width. Before solving, here are the 3 key formulas. First, the condition for minima, spoken as a sine theta equals n lambda, whereas slit width, lambda is wavelength, and n is 1, 2, 3, and so on. Second, the linear width of the central maximum on a screen at distance d, spoken as 2x equals 2 lambda d over a. Third, the angular width of the central maximum, spoken as 2 theta equals 2 lambda over a. Here is an intuitive picture for a single slit on the left and a screen on the right. The slit width is a. The screen is at distance d away, and the central bright region on the screen has a linear width 2x. Problem 1. A light of wavelength 600 nanometers falls on a slit of width 0.1 millimeters. The screen is 2 meters away. What is the linear width of the central bright fringe? We use the formula 2x equals 2 lambda d over a. Let us substitute the numbers carefully and compute. Problem 2. A screen is placed 50 centimeters from a single slit. It is illuminated with 6,000 angstrom wavelength light. If the distance between the first minimum on either side of the central maximum is 5 millimeters, that is, the linear central width 2x equals 5 millimeters, find the slit width a. We rearrange the same formula to a equals 2 lambda d over 2x. Now substitute and compute the slit width. Problem 3. light of wavelength 500 nanometers passes through a slit of width 0.2 millimeters. Find the angular width of the central maximum. We use 2 theta equals 2 lambda over a. Now we substitute and calculate the angular width in radians. To summarize, linear width scales directly with wavelength and distance to the screen, and inversely with slit width. Angular width depends only on wavelength over slit width. With these 3 compact formulas and careful unit conversions, you can solve most single slit diffraction numericals with confidence.